In this video, you'll see what happened when I rebuilt my latest solar-powered aeroplane and upgraded it with a much improved electronic system, ideal for long-duration missions. I've been working on this complicated engineering challenge for a few months now, trying to build a solar-powered RC plane with the ultimate goal of generating more power than it consumes to stay airborne. But the first test flight didn't end too well, as the onboard electronics failed mid-flight, causing the plane to come crashing back down.
Some of our electronics might have just gone a bit wrong.
After that devastating crash, we had to find out what had caused it. So we would carry out an air crash investigation, develop a new, more reliable power system, and completely rebuild the plane before thoroughly testing it out both on the ground and in the air to see if we'd made progress towards our ambitious target. Straight after the crash, we jumped into a thorough investigation to pinpoint the exact cause of the disaster. The plane had a fairly complex power system. First of all, the cells were attached to the MPPT charge controller, which managed how much power was sent through to the main flight battery to keep it charged up at the optimal rate. The battery power was then routed back through the MPPT to the rest of the RC electronics that you would usually find in an RC plane. We carefully recreated the conditions of the failed test flight to see if we could replicate the problem. That's when we discovered something quite alarming.
Well, there we go.
A built-in battery disconnect feature that we'd been completely unaware of. Because we hadn't done any proper bench testing before our first flight, we had no idea that this feature even existed. As the battery has steadily discharged, with the sun levels being quite low by the time of the crash, the MPPT decided to shut off, causing the plane to shut down mid-air and fall out of the sky. So the big question was, could we design a simpler system without this point of failure?
With this, I was thinking solar panel, and then that would then go into the input of a voltage regulator.
Helpfully for us, Matt from the YouTube channel DIY Perks came to lend a hand. If you've watched Matt's channel, you'll know he's just completed building the world's largest iPhone, so it's safe to say he's pretty skilled when it comes to electronics. Matt had the bright idea of using a voltage regulator set to output the same voltage as the 4-cell LiPo flight battery, which would completely eliminate the need for an active charge controller. The way this system would work would be much simpler than before. Power from the solar cells would go to the voltage regulator, which would then send a steady 16.7 volts to the battery, and this battery was wired in parallel with the rest of the RC electronics. When the motor isn't running, power is drawn directly to the battery. When the motor is running, power is drawn to the motor, with the excess going to the battery. It was a super simple way of charging a battery, as the differential voltage between the battery as it started to discharge and the 16.7 volts from the regulator would naturally ensure that it was kept topped up at all times, as long as the motor wasn't drawing too much power. To test all of this out on the bench, we used a higher voltage lithium polymer battery to charge the smaller 4-cell battery.
So it is charging it, the voltages are equalising. I feel that that's fairly normal. We are charging that LiPo from that one. So if this was solar, that would be literally charging from the sun.
That's good. That's looking good.